So thanks very much for the introduction, and thanks for the opportunity to speak on this. When we were setting up, like last week, checking the IT out, Ollie and I were talking, and we realized that we met in 2004, I think, in the St. Petersburg conference, I think. And the reason I mention it is it's kind of a landmark event because, that was kind of when the nanodiamond film and the nanodiamond particle people just collided. And before then, a lot of the growers were messing around with nanoparticles. But to be honest, if you look at the work that we'd done, it was pretty poor because we hadn't read the literature. And you could see really in this conference that we hadn't appreciated that these nanoparticles were in aggregates, and we didn't really understand anything like zeta potential. And so, it was a really important moment. And I think, I want to go back to a lot of that in this talk. So, I'm from Cardiff University. I'll show you my group towards the end, but I'm going to go through some of the things we do. My main motivation is probably still films.
Ollie, sorry to interrupt. I can only see half the slide. Has everybody else got that, or is it my problem?
We see a full slide.
I think it's your problem.
Sorry, it's my problem. Okay, apologies.
Right, yeah, it's another professor, So, okay, right. So anyway, are they changing? Okay, right, we're okay. So just a super quick overview. I mean, we're very strongly driven by industry, actually. Even though I'm in a physics department, I'm still an electronic engineer, and so most of the stuff we do is quite strongly related to an application. It might be a distant application, but it is. So we do a lot of like film growth, from filtering, with things like Huawei. So we're growing thick films for them and polishing them, or the sort of superconducting work we do. But what we tend to try and focus on is making materials for people that they can't buy. So if you can buy it, don't waste your time coming to us because they're probably better at it, right? If they're commercial production line, right? But we do a few weird things as well. I mean, we've focused a lot of time recently on looking at thermal management of electronic materials, so trying to grow on gallium nitride, stuff like that. We make electrochemical electrodes for people. We do a lot of MEMS still, and we still have this interest in diamond particles separate from the films. Actually, they're kind of fun to play with. Recently, we sort of moved into this sort of harsh environment thing, which I guess it's not diamond, so most people won't like it, but it's kind of interesting. Diamond graphitizes, unfortunately. Okay. So super briefly, I mean, as a film group, we have 4 reactors growing. I mean, we have 3 SECI systems and 1 home build. So, our workhorse is this kind of SECI 6500 system that now this one here is, it's actually called Boxer. So it's a workhorse, right? Like Boxer from Animal Farm. And it's about 10 years old, actually. And it's, in 10 years, it's failed once, which is impressive. And, we have quite a big setup for different gases and stuff. So, if you want silicon vacancy or nitrogen vacancy, we have a setup to do that. We spend a lot of time on, again, specific things that you can't buy. So we do a lot of in situ monitoring, stuff like that. With the nanoparticle stuff, again, we try and focus on stuff that's not available. So we make our own nanodiamonds. What we do is we'll grow the diamond film with nitrogen or with silicon, and then we'll smash it into bits. So we do this for a few people. Obviously we're not massive nanodiamond experts, but we do a little bit of sizing and zeta potential and stuff like that. And the surface group stuff, I mean, is pretty minimal. We do that mostly as collaboration. Like we tend to work with physical chemists on that. And I mentioned here the chemical mechanical polishing. I mean, I won't mention it again in this talk, but it's a critical part of what we do because the problem is that diamond, if it's not single crystal diamond, is fundamentally rough, and you really need to deal with that for a lot of technologies for industry to take you seriously. So in MEMS or wafer bonding, it's absolutely critical. And the other reason I put it in is that it's actually, a lot of the work is nanoparticle based. We need to look at colloids and slurries and stuff like that in development. So it's tricky. So this is an example here of stuff, we've taken an NCD film and made it look like silicon just by planarizing it. It's not actually that easy. It looks easy, it's not. And then we have some clever clogs people in my group that do low temperature stuff that I'm really going to glaze over very quickly because I don't know much about it. But, all the superconductivity stuff is done at low temperature, obviously, but this talk isn't really about that. Okay. Right. So I'm going to have like 3 or 4 slides on films before I go into the particles, because I think it sort of sets the scene. For a lot of diamond properties, most people are quoting single crystal diamond properties, right? And you've got to be very careful with that because they do deviate, right, when things get small. But you know, if you're interested in electronics or whatever, just go and buy this. You know, go to Element 6 and buy the super awesome grade material they sell, and be done with it. Don't come and talk to me. I can't compete with this. You know, we do a little bit of the window stuff for specific applications. Again, you can buy it from people like Element 6, Diamond Materials, DDK, or whatever. But you know, what we really focus on is kind of this side, is that, you know, it's slightly thinner again. So we tend to be interested in substrate supported because we're trying to create, you know, disruptive technologies that are a bit cheaper, and the nanodiamond stuff. But the reason I put the slide in is, of course, as the Raman gets worse as you go to the left, right? The part of, you know, as it gets smaller, you get more and more sp2. So watch out for that, right? You can't ignore this. And yeah, sorry for the super busy slide that normally Richard would tell me off for, but there's a point to it. If you look at films and you reduce the grain size, the properties change a lot, right? So on the top left here, what I've done is I've replotted some data from Fraunhofer years ago, where we varied the properties of the film and looked at the Young's modulus. And you can see that basically as the grain size drops, the Young's modulus just drops. And this is important because if you get below a certain size, you really shouldn't be wasting your time with diamond, right? If you're down at 750, go and get a silicon carbide wafer, it will beat it. And you can buy them, you know, 6-inch wafer silicon carbide, no problem. Beneath, I've got the results from the Martin Kupel's group in Bristol on thermal conductivity. And it's kind of the same story. You get below a certain size and the thermal conductivity just precipitates, right? It just drops completely. And, you know, this is physics. You can't get around this problem. So, you know, the mean free path for a phonon in diamond is of the order of microns, right? So if your grain size is smaller than that, you do not have the thermal conductivity of diamond. And if someone is claiming they do, then we need to rewrite physics textbooks, right? You know, so this is something that I think you need to be very, very careful about. And the same with the electrical conductivity. So this is years ago, some work from Walter Schottky, who was collaborating with Jose Garrido at the time. And what we did is we grew a load of nanocrystalline diamond with boron, we measured them, and then we compared them to single crystal. And of course they're worse. I mean, you know that, right? But you know, at the higher conductivities, you don't see so much because it's all hopping conductivity or whatever, right? But when you go into valence band transport, of course, the single crystal demonstrates high mobility, but the nanocrystalline will never do that. So you see a drop off in conductivity. So my main point here is that, you know, just be very careful with reports of bulk properties in nanofilms, because this would require us to rewrite physics textbooks, right? I mean, if you really had a high mobility in a nanocrystalline material, that would mean that your mean free path is substantially bigger than the grain size. It isn't, right? Somebody made a mistake, right? But the other thing is that there are some weird effects. I don't want to be too depressing. There are some fun things that happen too. So I'm just putting this in as a plug for Georgina's recent paper, is that actually, you know, in superconducting materials, you know, it kind of gets interesting, right? So if you make superconducting nanodiamond, there's actually a benefit, is that you can make small superconducting devices that behave much better than the equivalent in single crystal. And the reason for that is that, you know, in a nanocrystalline material, you have almost like each grain acting like an individual superconductor, right? So the boundaries, you have something called a phase slip. I don't want to go into this talk, and check out George's paper, just submit to Carbon, very nice. But the upshot is you can actually make devices such as Josephson junctions with much bigger dimensions than you can with a single crystal. So if you look at the history, you know, we published a SQUID paper about 10 years ago on NCD, and the single crystal guys still haven't matched it, right? And the reason for that, I think, is this phase slip phenomenon. So it's not all bad. So what I'm saying is that some nano stuff is fun. So we'll come back to this in the crystals in a minute. Sorry, the little particles. Yeah. Okay. So my very old nanodiamond particle slide. So maybe we go right to left here, right? So I think there are 3 types of nanodiamond, right? They're the ones that are kind of big diamonds that have been smashed, right? You know, the submicron grit, as I call it. And these are the ones that, as far as I'm concerned, are bulk, right? They're just small, right? Not very interesting, but you know, very interesting to quantum people or whatever. But actually, it is just a smashed diamond. There's the detonation nanodiamond, which is like this kind of amazing, you know, Russian discovery of like, you know, blowing stuff up and finding little diamonds in the mess, which is incredible, with like, you know, a very small particle size, you know, around about 5 nanometers or whatever, but with a much higher sp2 content. And then there's these things that I hate called the diamonoids. So there's a reason I hate the diamonoids, I'll come back to it, but the diamonoids are an off product, you know, they're mostly found in, you know, oil refineries or whatever. And the issue really is that they're really small and interesting, but you can't really get them. You can get adamantane or diamantane or anything bigger, you have to sell your soul to Chevron, right, to get them. So, you know, it means that research in them is pretty limited by that. And there's another reason I hate them. So I'll show you why now. Where is it? So some years ago, Suman and I spent way more time than we should have done trying to make them work as nucleation sites for diamond growth. So what we did is that the story goes is that adamantane, right, the smallest diamond, you would think, oh, cool, that must be the greatest diamond seed imaginable, is actually a terrible diamond seed. And the reason why is that it sublimes at about 250 or 280. So, well, we got into a gang with some guys in Switzerland who basically attached some molecular tethers to it, so we could photo attach it to the silicon 111 face, which is, super clever and everything, but honestly, it's really, really flawed, because the problem is the silicon always oxidizes. So you're trying to remove the silicon with the, HF, and then you're trying to quickly photo attach this molecule and then grow on it. So the upshot is that we spent a very long time, playing around with it, and we got it to work occasionally, and the problem was on the wafers, you find it's very patchy because the wafer will be oxidizing. So when you actually grow well in some places and bad in others, right? And so this is not really very useful. I mean, the interesting thing was, though, is in places that had enormously high nucleation densities, like higher than you see with detonation. But the problem is, like, detonation gives you a very high nucleation across the entire film, right? So just don't bother. So this is why I hate diamond. I wasted 2 years of my life on that. Anyway, so going back to the bulk diamonds, right? So let's take a big diamond and smash it. That's what this is kind of fun. So the way we do this is that we just mill it in a standard high energy mill. So this is a Pulverette 7, I think, premium line. They're not even that expensive. But to mill the diamond, you really need it to cut it down before you do it. So if it's more than 200 microns, it won't mill. Or it will mill, but it will mill a lot of your mill, right? And so this is a problem because diamond is super hard. So you try and mill it, and it's milling your mill. So you have loads of material afterwards. So the joke we have in the group is you mill, you weigh your diamond, then you mill it, and it's much heavier because it's milled and mill afterwards. So you have to remove all this crap. So I won't go through all the conditions. You can look it up in Liar's paper here. But the thing is, what I would say is be super careful if you're going to do this, right? Because these mills are pretty dangerous. They can overheat, they can explode, and all sorts of nasty things. So just be a bit careful, or send us an email if you're not sure. You need to let them cool down. Don't go turn everything to 11. It's not good. So after the milling, you have all this like contamination. So most commercial milling is steel based, or I think it is from the stuff that we've looked at. And the problem is that if you do that, then you have ion contamination. And if you're doing magnetometry, this is a big problem. So some of the people we work with, especially the group in Warwick, they can't live with that because they want to do magnetometry. So they need to be sure that it's not there. And we did a lot of playing around, and we never got rid of it. Whatever we tried, we always ended up with something in the XPS. You can see here, this is the ion peak here, and it might even be iron oxide. I don't even know. I'm not a chemist, so I'm sure some better chemists can remove this, but we can't. We tried very hard. And so we kind of gave up and went to silicon nitride for certain applications. And this way we're able to, to get, iron-free material. And I think is it the next slide? 1 second. Oh no, okay, in a couple of slides, I'll show you why. So when you've milled your stuff, you centrifuge it, and then you look at like what you've got. So the main technique people use to do this is dynamic light scattering, right? Which is pretty standard, and it's very, very good. It's very effective, but you've got to be very careful, because the problem with light scattering is that, the intensity of scattered light is proportional to the size to the power of 6, right? So if something is 10 times bigger, it scatters 1,000,000 times more light. And so the upshot of that is that when you put a sample into your DLS, is if there are a few big particles in that sample, it will totally swamp your spectrum. And that's kind of what you're seeing here. So the blue fellas here are the DLS spectrum, and the red ones are what we call NTA. Now, NTA is another light scattering technique invented by a British company called Nanosite, that's now bought by Malvern, actually, another British dynamic light scattering company. You see what happened there. And what they do is they create a kind of plane of scatter with the laser, right? So they basically, what they do is they have a scope with a very, very fast camera looking at the laser scatter move as a function of time. And then they track the motion of the particles with a computer. And then you can build up a distribution of the actual particle sizes. And so the nice thing about that is you can see components underneath the DLS spectrum. But this kind of horses for courses, because this, this technique won't work with too strong concentrations. Then you just have to use DLS. Also, you can't see below 20 nanometers, so it's useless for the detonation material, unfortunately. But this movie kind of illustrates what's going on, because you see this particle here, right? This is a bit big and it's flaring, right? So in the DLS, this would be dominating the spectrum. But in NTA, we can see the other stuff at the same time. So there are advantages to that. But anyway, if you play all these games and centrifuge super fast, you get down to about 50 nanometers, something like that. So this, you can go quicker than this. This is not particularly fast on a centrifuge, actually. So we played this game with the SIV years ago in the WASP consortium. And so this is the Raman after milling with steel. So we didn't care about steel at this time, I think it's a bit before. This is the PL spectrum of silicon vacancy emission at 741. And now I realize this plot shouldn't be here because actually this anti-bunching, I'm pretty sure is a film before milling, not after. I'd have to check actually, because there's a long story here. Oh, maybe it's in the next slide. Hang on, let's just bring this one up. Is that within this project, we had a lot of dispersion with silicon vacancies. So we see a big movement in the zero photon line and a big also movement in the peak. And my recollection was that we didn't see single photon emission from ours. And I've just realized we did, but it was very weak. Yeah, here you go. So this is us here, the CVD ones, but they're way less intensity than some of the other ones. So there's still a big problem with silicon vacancy, getting strong emission and single vacancy at the same time. And I think, you know, these guys here, you know, Basher Group would be able to tell you more about it. So I just refer you to their paper. But the other point I would make is that the HBHT material seems to be much better. So the Davidoff group seem to be able to make much better silicon vacancy stuff than we can at the moment. Still not entirely sure why, but, you know, HBHT is kind of magic. So, you know, okay. Hang on, here we go. So the other reason why we make particles ourselves is for things like cars. So in some techniques, you need really, really high purity. So CARS stands for Coherent Anti-Stokes Raman Spectroscopy. And what it really is a nonlinear way of looking at you know, particles, right? So if you think that you could just look at a diamond particle moving through a cell, right, just with the Raman signature at 1332. Now the problem with that is that the intensity of the Raman signal is just proportional to the number of molecules. But in CARS, it's nonlinear, it's number of molecules squared, right? So you get much more intensity. So you can see here, this is a group from Cardiff, it's not my group, the Borri Langren group. So Borri, Paolo Borri is from biosciences, Wolfgang is from, he's a photonics guy in physics. And here they're tracking these particles move through a HeLa cell, which is kind of cool. So they can simultaneously look at this wavelength, and then they can also look at the, you know, the cell at 2850. I can't remember what 2850 is. I think it's a lipid, but I'm not sure. The issue is though, if your sp2 content is high, you've stuffed, it will just heat up the particle and it will explode. So you have to be a bit careful with that. And the other thing that I wanted to show is Gavin Morley's stuff. So we didn't do any of this work here, right? We just made the particles. So I refer to Gavin's paper here from his group. And what he does is this sort of, you know, super clever, you know, levitating the particle in a vacuum system, right? So what Gavin's trying to do is to levitate a particle and put it into a position, a superposition of, you know, a quantum superposition, right? It's super clever. And he wants to, I think he wants to use the magnetometry at the same time, so he can't deal with the steel either. And the thing was is that he tried a lot of commercial particles, and they would just explode. So you can levitate them, but as soon as you pump them down, they just catch fire, right? And the reason for that is that the absorption of the particle is absorbing the light, and they'll just heat up. There's nowhere for the heat to go, right? If you're in air, you're okay, but as soon as you go into vacuum, you've got a problem. And the way you get around that is you buy the nicest diamond you can find from element 6, right? Which is prohibitively expensive, and then you smash it into nanoparticles. That's basically what we did. And you can see this is a standard micro diamond stuff here, about 150 ppm nitrogen. And down here is E6, you know, superhero electronic grade, you know. So we made that into nanoparticles, which was a bit crazy and very expensive. Okay, so going on to the detonation stuff, which is, I think, the more interesting stuff, actually. So I don't know, I think most people know about this stuff, but if you don't, this is really worth reading this paper by Danilenko, right? It's a really good history, and I stole his phase diagram because it's super useful, because it kind of explains how it works. You know, for a very short period of time in a detonation, you have this high pressure and temperature that gives you your diamond, yeah, for about a microsecond, and you get about 5 nanometers. The problem is for the rest of the shock wave, you get stuff that isn't diamond. And that's really bad, because when you go and look in your TEM, you have loads of little particles stuck together by all sorts of rubbish. And what you do then is you go to Anka's paper, because she's got a nice drawing. Yeah, there we go. So this is from Anka Kruger's paper, which you should also read, by the way, if you haven't read it. It's very good. And this one is directly about what I'm talking about, is these little nanoparticles are very tightly bound, which is the point of a paper. So I think Anka was the first person to really mill it down into the small particles, which made all the difference for diamond seeding, actually. But the key take-home point is that there's 20% of the atoms are actually at the surface. So you have, you know, 400 meters squared per gram surface area. It's really enormous, right? So when you think about how these materials behave, you've got to think about the surface, right? Okay, so years ago, I mean, we were using this milled material from Professor Osawa, which is very, very good. So if you're a diamond grower and you just want to grow thin films, just buy it. I mean, there's several people selling it. I'm sure Ollie also sells it, and it works great. You don't need to make it yourself. It's a waste of time, honestly. But you know, we were a bit worried because at the time there was only one person making it, and we were a bit, what's going on here, you know? So, and we really needed it to make MEMS. We really needed to grow thin films, so we need very small nanoparticles. So we came up with this hydrogen annealing. I should be honest and say we didn't really come up with it. I mean, I knew Jim Butler was doing something like this, but he'd never said what it was. So we had to kind of guess what he was doing in the lab. And then we came up with this thing where I think it's similar to what he does, is that we just heat the particles in hydrogen, disperse them with ultrasound, and then we centrifuge them. Bit strange. Why does that work? Come back to that in a minute. So if you do that, you know, even after just heating in hydrogen, they already break down a little bit into smaller particles. But when you centrifuge out the big fellas, remember what I said about DLS? If there are big particles, you can't see the small ones because the intensity is all coming from the big ones. You can see the small particles. You just get a big centrifuge. And then actually now you have a really nice solution of a few nanometers. And if you look at the FTIR, I mean, this is the thing that was really interesting and caused a lot of controversy and fights over a few years, was that what actually happens is, I'm going to skip through all the boring peaks and just go to the, yeah, here we go, is that when you anneal in hydrogen, is you're able to remove these COH groups from the surface. Yeah, you reduce those, and then you see the CH groups, right? So this is where it gets really interesting. Because, you know, this doesn't make any sense, okay? Because, you know, hydrogen has a, you know, a dissociation energy of 4.5 eV. So if you take a diamond and you heat it in, you know, in 500 degrees in hydrogen, nothing should happen, right? So this started a bit of a discussion. I mean, I did actually mention this in the paper that didn't make a lot of sense, but it, you know, I just said it's something to do with sp2, which is not a very satisfying answer. So this started a discussion between myself and Xiaoling Chen, or Charlie, over some years, because, you know, Charlie's objection was that if you know, just measure FTIR in air, you know, how do you know it's not surface contamination, right? Which is a good objection, and he is an FTIR expert, so fair enough, you know. So we sent some material to Charlie, and he basically put it into UHV and did the same thing and said, okay, you do actually have CH bonds, I believe you now. I didn't get an apology, by the way, but anyway. So, but the thing that he did afterwards that was super clever was he put the particles into a UHV system and then looked at a mass spectrometer as he heated them up, yeah? And so at about 300 or 400 degrees, he started to see, you know, 36 AMU, right? Which he attributed to C3, or it could be. Thing is, lots of things add up to 36 AMU, right? But, you know, it could be some oxygen-based thing, but something is coming off the particles at that temperature. And this is the same temperature at which we start to see the CH formation, right? So that's super interesting. This is a really good paper, by the way, by the Dongwha group. And so they came up with a basic model. So obviously we can't prove this because you know, you can't really look at this. What you could probably do is something like cavity ring down spectroscopy to see if you can see C3 absorption. But I suspect the signal is so weak, you would need someone like Mike Ashford to be able to do that. It's pretty special. So, you know, the idea is that you have your UGE, there's like finite concentration of sp2. You know, you heat it up, it forms C3. The C3 could easily crack the H2, which can then terminate the surface. Like I say, I can't prove that, but it's possible, you know. So that was super interesting. But the other thing that, you know, a consequence of that is that it also works for nitrogen. You can play the same game. So if you take these detonation materials and you heat them up in molecular hydrogen, sorry, nitrogen, excuse me, you can get all sorts of weird amine terminations that are actually normally quite difficult to make. So I think this is quite interesting and underappreciated paper also from the Dongwha group. Yeah, I mean, this is a bit surprising, you know. Okay, so I'm going to slow down super quick and a quick trick and talk about the positive zeta potential because I think it's going to be controversial, but we'll see. So if we think about the smallest diamond particle, just the detonation stuff, right? When you normally buy it, it's been purified in a lot of acid, or you burn it in air. Either way, there are a load of CH groups on the surface. Sorry, COOH, yeah? COOH, and OH, right? Now, if you put that particle into water, it can become deprotonated, right? That's pretty standard. So you see in a lot of materials, they express what we call a negative zeta potential, is that because they have these COH groups on the surface, when you put them into water, the COH becomes deprotonated, so H plus goes into the water, right? Leaves behind negative charge, yeah? Another upshot from that is because the H plus has gone into the water should become more acidic, right? I'm gonna come back to that in a second. So you see that in diamond, and it's not controversial, and we, lots of people saw it before us, so what, right? Not very interesting. But then when we hydrogenated, what happened here? It's become positive, right? That's weird. Now, we know from the FTIR that we are removing the COH groups, right? So you might expect it to go neutral, but why would you expect it to go positive? Yeah, this is a different thing. This is, if it went to the middle, I wouldn't be even talking about this. It'd be like, yeah, that's boring, okay? So what is this? And this, I think this has been a controversy for 10 years, and I don't think we're any closer to the answer. Well, a little bit. But at the time, I speculated in this paper, it's something to do with the sp2, because I tried it on bigger particles and it didn't work. That was, my hand wave argument, not a very good one. But more recently in Cardiff, hang on, yeah. So Laia Guinness was working for me, she's now in Uppsala, a PhD student, came up with the idea, is like, why don't we try and take the particles it doesn't work on and anneal them to create sp2 and see if it works then. And it works, right? So what you're seeing here is these are 50 nanometer particles. If you try and heat these in hydrogen gas, nothing happens, or very little, right? Or certainly if you do it at 100 nanometers, nothing happens, right? But if you then anneal them in vacuum at 1000 degrees C or so for a few hours, temperature, there's an error bar on this because we're never really sure about this furnace temperature. It's high, right? It's 1000, maybe a bit more. What you see in the TEM is you start to see, of course, all this graphitic stuff start to appear, these sort of graphene-like shells or whatever you want to call them. And then if you try and heat them in hydrogen, you start to see the CH stretch. So it starts to react, right? So that's a red flag to me. It's like basically you need the sp2 to drive this reaction on the surface, okay? If you then go to the Raman, you also see, I won't go through all of it because Raman is really boring, but basically, you see in part, the ones that we've annealed, you see this G peak, right? This 1582, which is directly related to these rings, right? These the things that we're seeing in the TM. So this is just for the people that don't believe the TM. Fair enough. Yeah, I know what you mean. So basically, if you create these, you can make it react. And so what happens to the zeta potential? Well, if you don't do this annealing step, you can't create a positive zeta potential on these materials, on the larger grain size, right? Now, small caveat, some people have claimed with a hydrogen plasma you can, but we also did that back in Germany and never published it because we were convinced that it was actually graphitization because we saw a change in color in the particles, so we never actually said anything about it. In this case, if you do a remote hydrogen plasma, it doesn't go positive. So if you try and remove the plasma contact from the sample, I don't see it going positive. I see it going neutral, which is what I expect actually. But if I generate the sp2 and then anneal it in hydrogen gas, it goes positive, right? So I think this is really important because we don't see this positive zeta potential without the sp2 bonding in this case. And the thing that really made it clear to me, well, maybe not so clear, but convinced me a little bit more, shall we say, is the basicity. So going back to the COH groups, let's just talk about the clean particles before we've treated them in hydrogen, right? They're COH terminated, right? You put them in water, COOH becomes deprotonated. So there's a negative charge on a particle, the solution must go negative. That's what you see as a function of concentration, is the particles, the more you put in, the more negative the more acidic the solution goes, right? So what happens in the positive case? Well, you see carbon basicity, right? So this is also very interesting because it means that you're making the sample go positive, but at the same time, you're taking protons out of the solution, right? That's basically what it means. And the thing is, if you do it on smaller particles, it's much more extreme. Yeah, you see here, so that the negative is about the same, but the carbon basicity is way stronger in the 5 nanometers over the 50 nanometers. And again, it's related to the concentration of sp2 on the surface. And so full disclosure is like, Angus group years ago saw this in Science and published it, right? And they attributed it to surface conductivity. I don't think so. I think they saw the same thing as us, but I think the reason is not true. So what happened is that they did again a hydrogen plasma, and I think you graphitize when you do that, and you might not see a great big difference in the Raman, right? It's not that sensitive. And the reason I don't think it's surface conductivity is if you take a bulk diamond and hydrogen terminate it, you don't see a positive zeta potential. So I'll show you that data, right? So here we do streaming potential. So this is almost the same as zeta potential, but we're now doing with 2 large diamonds, right? So I've got, like, in this case, 70 micron thick films. So this is Suman did this years ago. Henry's repeated it on much thicker films, with bigger grains, and sees the same effect. Is if you hydrogen terminate, you do not see a positive zeta potential. You see neutral, right? And so for me, that's a red flag because there's almost no sp2 on this material. And if you don't believe this data here and the repeated stuff from Henry, This is some stuff from Jose Garrido from 2007, who actually saw the same thing. And I think we all missed it because they've done a paper about something else. But he never saw a positive zeta potential, from hydrogen terminating, a bulk diamond. And the final thing, I think, on the positive zeta is if you go back to all the carbon black literature. So this was something I used in a big hand wave in the paper in 2010, saying, well, it looks a bit like carbon black, which I don't think was very satisfying at the time. But the thing is that literature has been seeing positive zeta potentials for 30, 40 years, right? And we know that we have sp2 on the surface of the diamond particles, so why not, right? So I took, in Germany, I took some carbon black and hydrogenated it, and of course you see a positive zeta potential. You only do this once, so it's very messy, it gets everywhere. And if you look at the literature that, people like the great Peter Bohm, one of these, the guys who invented the Bohm titration, they talk about this sort of protonation of the graphitic basal planes, which we're seeing in the TM. We see those graphitic things, and we see them in the Raman, right? So there's no reason why this can't be happening in the diamond particle. It's just not that clean. That's the point. It's really small. So I think it's, it's related to that. It's difficult to be absolutely 100% sure, right? I'm not sure if you ever can, but I think you can't ignore this. And certainly I think the surface conductivity argument will not work. So for the last few minutes, I just want to go through sort of applications, and apologies for the old data here, but I think it's still important to look at it. Years ago, I said, when we went to the St. Petersburg conference, the seeding was working really badly, right? So for the non-growers, what we're trying to do is take a silicon surface and just coat it with as many diamond particles as possible, right? But you don't want 2 layers, you want a monolayer, right? And you want it as as thin as possible and in size as uniform as possible. And we got 2 things wrong, right? It's one that we didn't know they were aggregated, which is a pretty big mistake, right? That's a big one. Yeah, hold my hand up to that. Got that wrong. There was another one, is the material was all cleaned in acid. And if it's cleaned in acid, it has a negative zeta potential. Oh dear, because your silicon also has a negative zeta potential. So if you look here, where we just characterize silicon dioxide, these particles are never going to stick to each other. They're repelling from each other. So if you try and do an AFM afterwards, what you see is this really awful nucleation here. So what you need to do is reverse the zeta potential. And the easiest way to do is just to heat hydrogen. And then you get enormously high densities. I mean, there's other ways to make this positive stuff. The stuff from Professor Osawa and Anchor that's been milled is also positive, and it works great. So if you just want to grow thin films on silicon, just buy it. Don't care about this talk. So what we also did is we played with the opposite. Other materials like aluminium nitride, where you've got to think about the surface a little bit. So what I'm going to say here is a big beware, because some aluminium nitride surfaces have the opposite zeta potential, but it really depends on the face of the aluminium nitride and whether it's oxidized. And so what I'll do is I'll just show you all the data from all our papers. Before I do that, I'm going to make a quick point that actually CA also did this, right, by using a polymer. So they coated the surface of the silicon with a polymer with the opposite zeta potential. So this is another clever way around the problem, right? So you can also do that. But just to show what we've done, I mean, on silicon, it's so easy now. You can just buy this from whoever, Osawa or Olio or whoever, and it will just work really well. Just do it. On aluminium nitride, you might want to look at what face you're looking at. We've done both faces, so you can just look and work out which one you need, and then you just go and buy that. Same with gallium nitride. It's never going to stick though. Sorry, just won't. Not for a long period of time. Certainly if you grow microns. Silicon nitride is an interesting case because actually the problem with silicon nitride is if you leave it on the bench, the zeta potential degrades across time. So we spotted that about a year ago in Henry's paper. It's a commercial company actually, and basically what happened is that their seeding went bad, and then you measure it with the streaming potential, and you can see that the surface is just getting contaminated. So if you immediately flash the surface just with an oxygen plasma, all of a sudden it works again. So that's what this paper is about here. We've also used this to demonstrate growth of very thick diamond on top of aluminium nitride, on top of GaN. So you can thermally manage the gallium nitride just with this interlayer. I think that's all I want to say about seeding. So just for the last few minutes, I'm already 32 minutes. I don't want to drag on too much. I want to talk about this virus filtration idea. So we were working on this for about a year, and then the COVID thing hit, which was topical. And so the problem with viruses is they're really small and quite annoying, right? And so we were looking at the water supply actually, but now we've moved on also into air. And the issue is that really, if you want to remove something let's just take something annoying, like 50 nanometers, that's pretty annoying to filter, right? You can't really just shrink the pore of the filter because that means you have no flow. So the filter's not very useful, right? So if you look at the commercial sector, companies like 3M, they have these masks that are actually electrostatically charged, right? And they're not to filter out viruses, they're for building sites. And the reason is that if you've got a guy carrying around, doing hitting loads of things or whatever, picking up heavy things, they need to be able to breathe, right? So you can't just restrict the flow. So what they do is they use larger pores and they charge them, right? So we were looking at this, but on a much smaller level, can we go smaller and then pull out the viruses, right? So, viruses are very variable. I mean, this nasty pasty here is almost a micron Ebola, but I mean, the SARS one is much bigger, right? Like 120. So hang on, next slide, I think. Are we not? Sorry, my computer's being childish. Yeah, so yeah, COV2 is basically, let's just say it's 100 nanometers, something like that. But the thing is that because it's a particle, basically, as far as we're concerned, it has a zeta potential. So, and the other thing about viruses is they're always aerosoled, right? If they're not aerosoled, they're not actually effective. They're not going to hurt you. So that means they're always in water. So you can exploit the zeta potential. So most viruses are somewhere between 3.5 and 7 isoelectric points. So this is just where the zeta potential curve crosses 0. So that means they're mostly negatively charged, okay? But the problem is, like, look, here's my little cartoon, right? So Jerome made me a little 3D version of the virus here. It's way smaller than the pore, right? This is the quartz filter here. You've got like 200 nanometer pores. Any smaller than that, you've got no flow, basically, right? So what are you going to do? So, the question is, can we charge them, right? Can we coat them with the diamond particles and switch the charge of the membrane? Yeah. And I guess I wouldn't be giving this like slides if you couldn't, right? So what we did is we took a quartz membrane. So here's a quartz filter, right? Standard quartz here. And this is what it looks like under the microscope. So you can see that the pores in this membrane are really, really big, right? The virus will go straight through here. We've tried it. It's not good. This is what they look like under the TM, and this is what they look like when we coat them. So we actually coat them and then we do a reaction. I can't say what it is because we haven't submitted this yet, but it's pretty obvious. So, what happens when you do this? So are we able to get enough on there to switch the zeta potential? And like, obviously, yes, because otherwise, why would I be presenting it? So this is the zeta potential of a quartz filter here, right? So this is measured by our streaming potential apparatus. You can put a bulk sample and measure it. And then Henry just keep putting diamond particles on it until he can flip the potential over, right? And so now we've got a very strong zeta potential. So this is really important because, to get like 60 millivolts in positive zeta potential is very, very strong. So I don't know of another material that expresses it that strongly. Like diamond is quite unusual, right? So we've looked, I've got a few on the bench actually from CMP, like Illumina, MGO and Syria, and they tend to be more around 20 to 30 millivolts, which means it's way weaker. And also their pH range is way smaller. So it's not actually that useful if you want to try and pull out these things from water. So we load them onto the filter, we react them, and they're super stable. Oh yeah, so this one here, this is the really exciting one for me, is that Henry here did the most boring experiment imaginable. We just keep pumping water through it and measuring the zeta potential over hours and hours, whatever. I don't know how long it took, I don't want to know. And you can see here, this is all the data points. And if you zoom in, this is the number of experiments he's performed and showing that the zeta potential is not changing. It's really stable, yeah? So this is super cool. So does it actually work? So I can't show you the virus data because again, it's not published, but I'll show you the data that we've already shown in Hassel, right? So what we did before is we took a virus analog. So we took acid black 2. And the reason we picked that is it's super small. It's like a nanometer. So acid black 2 is a well-known industrial contaminant, and it's very hard to remove from the water supply because it's super small. So what we do then, we know it's negatively charged, and we just basically see, can it go through the filter? Well, if it's a quartz filter, it just goes straight through. You can't stop it, right? But if you reverse the charge, all of a sudden, you're able to pull out the acid black 2. So it may look like it's deteriorating here, but this is, of course, fouling, right? We're using very, very high concentrations here. So if you do it at virus-relevant concentrations, there's no problem at all, yeah? So this is just acid black. It works pretty well. And the really fun thing about this is if you go back to this is what the filter looks like, right? Is that, this acid black molecule is absolutely tiny compared to these pores, right? And we're pulling it out just by the zeta potential. I think that's pretty cool. Okay, so, just to summarize, you can make your own nanoparticles. We do that by smashing things and breaking other people's diamonds, especially element 6. Yeah. The silicon vacancy for us is still tricky. Like I say, the Davidoff group have much better results than us on HPHT. Most of the commercial stuff is steel milled, so be careful if you're doing magnetometry, or find yourself a very good chemist. So don't ask me. You know, and these diamond surfaces are super reactive. When the smaller they get, the more weird they get, right? So be really careful about that, because it's this sp2 thing, you can't ignore it. And like I say, with the positive zeta potential, you only see that with hydrogenated material at the same time as the sp2, and it comes with the basicity at the same time. So for me, this is a red flag. You know, it's sp2 related. And the cool thing about it is you can exploit this. So like I say, not all nano things are bad, right? You know, the positive zeta potential means that we can self-assemble them on silicon wafers and grow super awesome thin films. That's great, right? But it also means you can do things like pull out viruses. And I'm sure there's loads of other things you could do with them if you thought about it. So I think, you know, I think what we're missing is that in the positive zeta potential, it is way, way stronger than other materials, right? Everything I've looked at is weaker than diamond in this, you know, this expression of positive zeta potential. And I think that's unusual. We need to look more into it. So finally, I want to obviously acknowledge my groups. There's loads of people who've done loads of work here, and I've just put up the people that are specifically related to stuff that I've shown. Obviously, we work with a lot of other people, and what I also need to do as well is to acknowledge the people who pay for it. Yeah, that's important. Yeah. So that's it. Thanks.